Okay, Curtis Bright from the University of Windsor is going to tell us about SAT solvers.
Thanks, Jeff, and thanks for organizing the session. I'm really looking forward to hearing what everyone has to say. So I'm going to be talking about SAT solvers. So first, what do I mean by SAT? So this is just short for satisfiability. This is the classic problem from logic where you're given a logical expression, you're asked to make it true, right? Find an explicit assignment to the variables, which makes the formula true. And we'll just focus on Boolean variables, so all the variables are true or false. This, in theory, makes the problem easy, right? Because you could just try every possible assignment. In practice, this is way too many. It's exponential in the number of variables. So, and we actually don't have any provably fast ways of solving SAT, but what we do have are known as SAT solvers, which are programs which have been designed to solve the SAT problem. And they have to use some kind of trial and error, but they use it in a very clever way. They don't just try every possibility. And in fact, they are so clever, and this is kind of mind-boggling, that engineers will go to the trouble of reducing a problem that they have to logic and then use a SAT solver to solve it because they're actually the fastest known way of solving problems from hardware and software verification. You know, problems which have nothing to do with logic even. Combinatorialists do this as well. So on the right here, I have an example of this. This is a coloring of the integers from 1 to 160 using 5 colors, subject to this constraint that if you have integers a, b, and a plus b, they're not all colored the same way. So you can easily check that this coloring satisfies that. What is also interesting, and this was shown with a SAT solver, is that you cannot extend this coloring up to 161. Right? This is the longest possible coloring, and this was shown by Marijn Hoyle in 2018 using SAT technology. As far as anyone knows, SAT solvers are the only technology that allows us to solve this problem. It was open for 100 years. They also produce unsatisfiability certificates. So when a problem has no solution, the SAT solver will produce a proof of that fact, and this proof can then be verified by a proof checker. All right, so this is an important property as well. So over the last decade or so, SAT solvers have been used more and more in combinatorial type problems. I've been working in the field for about 5 years, and here's some of the highlights of some of the problems which have been solved by SAT. I won't have time to talk about all of them. Obviously, I'm going to focus mostly on the first, and at the end of the talk, I will review our verifiable solution of Lamb's problem. This is recent work, and it won a Best Paper Award because this is kind of it was a high-profile problem, so it's a nice way to conclude the talk. But I want to start first with another coloring challenge. So this is similar to the sure problem that I mentioned. So the idea is we're going to have a fixed number of colors, and we want to color the positive integers such that if we have k integers in arithmetic progression, they're not all colored the same way. So k here will be fixed. An arithmetic progression is just a set of integers of this form, right? It's k integers separated, each one by a difference of b. Okay, so you might think you could do this. Maybe you think you can't. This was a famous theorem of van der Waerden about 100 years ago. So he proved that you cannot possibly find this coloring. No matter how many colors you use, no matter what the value of k is, if you want to color all the integers, positive integers, you have to introduce some arithmetic progression which has the same, all integers have the same color. Now, if you only focus on a finite set of the integers, then you can get away with it. So here's just a short example of that. Let's say we have 2 colors and we fix k equals 3. So in this case, we can color the integers up to 8, or the positive integers, right? From 1 to 8, as shown here. So this would be like blue, red, red, blue, blue, red, red, blue as a 0, 1 word right here. So it's easy to check that this satisfies the coloring condition. It's also easy to check that we can't extend this word, right? If we tried to extend it by a 0, you get 3 zeros in arithmetic progression. And if you try to extend it by a 1, you get 3 ones in arithmetic progression. So this word cannot be extended. So van der Waerden's theorem is that you can't find an infinite van der Waerden word, right? There has to be some maximum word. And so the van der Waerden number is going to be 1 greater than the maximum van der Waerden word, right? So it's going to depend on R, the number of colors, and K, the length of the arithmetic progression that we don't want to color the same way. So that means if we find, for example, the 0, 1 word I gave you, this is going to give us a lower bound on the van der Waerden number W23. It has to be greater than 8 because we have an explicit word of length 8 with 2 colors and avoiding arithmetic progressions of length 3 of the same color. In fact, this is the longest possible word. So W23, which we're going to show, is going to be equal to 9 using a SAT approach. So SAT solvers work a bit differently than your typical programming language. You might imagine you could run, well, you could run a search for all possible 0, 1 words of a given length. But the way SAT solvers work is they work declaratively. You give them logical facts about what the solution to your problem has to satisfy, and they will then search for solutions. So the way you communicate with them is you give them clauses. So something like this: X or Y or not Z, saying that X is true or Y is true or Z is false, right? So a general clause has this format here, and each of the L's here is known as a literal. Either it is a variable or a negated variable. So in general, they can't be arbitrary expressions. This is a very restrictive format. And you can give a SAT solver as many clauses as you like. Essentially, what you're doing is you're writing your formula in conjunctive normal form, because the SAT solver is going to try to satisfy every possible assignment. It's going to try to find assignments to the variables which satisfy all the clauses. Okay, so how would we code van der Waerden in SAT? Well, it's actually quite straightforward. I will just focus on with 2 colors. You can encode more colors as well. You'd need more variables. So 2 colors is the simplest. In this case, we only need these variables Ri. So Ri is going to denote that the ith integer is colored red. So if Ri is true, it'll be colored red. If it's false, let's say it's colored blue. And we'll also fix, for example, in that case, the simplest arithmetic progression is just 1, 2, 3. All right, so we know that we don't want 1, 2, 3 all to be colored the same way. All right, this is our coloring condition. So in particular, they can't all be colored blue, meaning at least one must be colored red. So we have a clause. 1 is colored red, or 2 is colored red, or 3 is colored red. We also know they can't all be colored red. At least one has to be colored blue. So either 1 is not colored red, or 2 is not colored red, or 3 is not colored red. This is also a clause. And so obviously there's nothing special about 1, 2, 3 here. You can just generate clauses of this format for any set of integers in arithmetic progression. So the complete encoding then is as follows. If we're trying to test if W2K is greater than n, then we fix some bound n and we consider all the arithmetic progressions on the range of the integers 1 to n. They're given by these clauses here explicitly. The arithmetic progression starts at a and is separated by a constant difference of b, and then it's in the range from 1 to n. So once we generate all these clauses, we give them to the SAT solver, and the SAT solver looks for a satisfying assignment. If it finds one, then this will define a 0, 1 word of length n, and this gives us a lower bound on the van der Waerden number. If it doesn't find one, it will produce a proof that such a coloring does not exist, and then you could feed this proof to a proof verifier, for example. This will give us an upper bound on the van der Waerden number. Now, if you want, well, here, there's a implementation in PySAT that I show you here. This is just it's a simple way to call a SAT solver. You can download, of course, SAT solvers from the web. There's competitions. You have to compile them typically, though. So they're not always user-friendly. So I chose PySAT because it's kind of a nice way to interact with a SAT solver. And you can download, if you have pip, the Python package manager, you can just install it. And then it's easy to use. So with 2 lines, we set up the solver. And then if we wanted to test if the W2K is greater than n, I generate all the clauses from the previous slide. So I have a double for loop over the indices a and b. And then I form the list of indices in arithmetic progression, starting from A with a constant difference of B of length k. And so range here is a built-in Python function to generate arithmetic progressions. Okay, so after that, we have our payload we call s.addClause. This is how you interact with the SAT solver. And the way it works is you give it a list of indices, of integers. So the integer 1 is going to denote the first variable. The integer 2 is going to denote the second variable, and so on. So this is going to be a one clause. Then I add a second clause, which I take the negation of all the integers in arithmetic progression. So in -1 will denote the negation of the first variable. -2 denotes the negation of the second variable, and so on. This is just the standard format of interacting with a SAT solver. So the first one tells us at least one is red of these indices, and the second one says at least one is blue. And then once we've generated all the clauses, we call s.solve. And the result then will be either true or false. True meaning we have an explicit assignment, and false meaning there is none. It's unsatisfiable. Now, if you wanted to determine the exact van der Waerden number, then, well, the simplest thing would be just call the SAT solver repeatedly. Right? We can have the bound n be very small at first, say n equals k, and then we look for a 0, 1 word of length n. If we find it, we just keep increasing n by 1 until we reach a point where we can no longer find such a word, right? Van der Waerden's theorem tells us eventually there's going to be some unsat instance. The very first time it's unsat will give us the exact value, W2K. And then you could just regenerate all the clauses from the previous slide, or you could be a bit cleverer and only generate the clauses, the new clauses, right? You don't have, all the clauses from the previous instance are still going to be valid. So you only need the clauses which include the new integer n, and then the code on this slide just does that. So let me actually show it to you. I'll run it. So I have a simple script here with some bells and whistles. So I start the solver with a timer, and I have n starting at k, and I increase n by 1 every time I go through this for loop. And then I have the set of generating all the clauses as necessary, as I showed on the previous slide. I call the SAT solver s.solve, and then I get a result, which is either true or false. If it's true, then what do I have here? I have an explicit 0, 1 word. And so you can call s.getModel to get the satisfying assignment. And then I wrote a function toWord, which is up here, pretty straightforward. It just reads the model and output, converts it to a 0, 1 word. So the way it does this is the s.getModel will return a list of integers. If they're positive, that's going to be a true variable. If they're negative, that's going to be a false variable. And then finally, if the result is unsat, then since we increased n by 1 every time, the very first time we get unsat, we get the van der Waerden number. I print it out with the time it took and exit the loop. So let's actually try running this. So I give the k value on the command line. So k equals 3, let's try. So here, almost immediately, we get 0, 1 word of length 3, which is a van der Waerden coloring. And then we prove that there are no van der Waerden colorings of length 9. All right, so that was fast. I mean, that's a simple problem. If we increase k by 1, k equals 4, it still runs very quickly. In fact, we get a 0, 1 coloring of length 34. And we prove that a length 35 0, 1 word does not exist. Do we dare increase k by 1 again and k equals 5? Well, you can see again it's quick up to 176. We get a word of length 176, then it's taking some time, and okay, we get a word of length 177. So that took a couple seconds. So I'll spoil it and say that this is actually the longest possible word on avoiding with arithmetic progressions of length 5 of the same color. So I'll stop that, but I have the results on the next slide. On my desktop machine, it took under a minute to prove that there were no words of length 178, where for k equals 5. So you can see very quickly we're able to get some non-trivial results. W26 is infeasible to solve with PySAT. This is a huge problem. It's able to give you some lower bounds. So it finds a 214 length word in under a minute, and it finds a 215 word in a couple hours. This is with no optimizations whatsoever. Just the exact implementation I showed you. So you can see there's a big jump there, right? SAT solvers can be unpredictable in their running times. Sometimes they'll run very well, sometimes they won't, and you can't always tell which until you actually run the instance. So the big result that I mentioned at the beginning of the talk was in 2008, Kurl and Paul used a custom SAT solver. So they did a lot of optimization trying to find W26, and the fastest way that they could find was indeed to use a SAT solver approach. And they used 200 machines for 250 days. So a huge massive computation, and eventually they found this result. W26 is equal to 1,132. So it was an amazing result. So just in the last 5 minutes or so, I'm going to talk about the work that I teased. So this is recent work on Lamb's problem first. So it's not over 0-1 words, it's over 0-1 matrices, but it's a similar type of problem. So we have two conditions that we want to satisfy when we're looking for these, what are known as projective planes. First, we want the matrices to be quad-free. They don't have any quads. A quad is going to be a rectangle submatrix with ones in the corner. All right, so you can see by inspection that these three matrices do not have any quads. And they also, you can see by inspection, they have this property that all of the rows and columns have the same number of ones. It's going to be one greater than what's known as the order. So if in order 2, every row and column has exactly 3 ones. Okay, and those are the only two properties that we have. So very simple to define these, what are known as projective planes. They come from geometry. They're the incidence matrix of a geometric structure. And they've been studied for hundreds of years. So lots of mathematicians have studied these. Lamb's problem is find a projective plane of order 10, or show it doesn't exist. This was a very infamous problem. And the reason being is because all smaller orders, that's to say 1 to 9, can be solved just purely mathematically. Either you find an explicit construction, or you can show that such a construction cannot possibly exist. All right, Lamb's problem is different. So order 10, as far as anyone knows, there's no simple solution. No one could find a projective plane of order 10, and no one could prove it didn't exist until work in the 1980s. So Lamb and his team of programmers solved this problem using a massive supercomputer search. So it was a huge result. It got a lot of press. Here's one of the articles that was written about it. And they were upfront about what they did. It wasn't a proof in the traditional sense, which raised some issues. They used custom-written software that was run on a single piece of hardware a single time. There's nothing to check, right? There's no certificates produced. So you either believe the result or you don't, right? So this is, you'd like something of maybe a bit more sound or verifiable. This is what we did. We generated the first set of non-existent certificates. So a third party can go and download the certificates and check them in a proof verifier. So as long as they believe in the encoding, and as long as they believe in the soundness of the proof verifier, they believe in the non-existence of the projective plane. So they don't have to trust the search procedure, which is very difficult to prove correct. So the encoding actually is not that difficult. I'll review it here. Basically, you're saying that for every rectangle in your matrix, at least one of the corners must be 0, because they can't all be 1. So if you let xij be true when the ij's entry is a 1, you're saying at least one of the corners must be false, right? So you have a bunch of clauses which look like this for every rectangle in your matrix. And then you can also encode the row and column sum constraints. You want exactly 11 ones in every row and column. You can reformulate this in a convenient format for a SAT solver. I won't go into the details, but there's lots of ways of doing something like this. So when I mentioned that there's a lot of trust for unverified searches, this is not just me being pedantic. This actually has real consequences, and we discovered this. There was as far as I know, two independent verifications of of Lamb's problem. First, Lamb's original search in the 1980s. There was another search independently done a decade ago, and they both just found the same result. No projective plane of order 10, which is what we verified. However, we did discover some partial projective planes of order 10, which were not discovered by the previous searches, right? They've reported some intermediate results. And in particular, one on the right here, this is a 51 column partial projective plane. And you can easily test that it satisfies the condition, right? There's no quads in it, and there's exactly 11 ones in every column. So this should have been found by the previous searches. And it was explicitly said not to exist by the previous search. So obviously, there must have been some kind of a bug in the search. And similarly, Lamb's original search also was missing some partial solutions. So in theory, if this matrix extended to a full projective plane, then we would have, it would have been missed by the previous search. So these things really do have, it just speaks to how difficult it is to write search code which is bug-free, right? And we know this. Everyone who's any use to computer program knows that they have plenty of bugs, even if the programs run every day, right? So the fact that you have a program which is running a single time, it's almost certain it's going to have a bug, unless you do a lot of verification. Okay, so just to wrap up, obviously I can only scratch the surface here, but I hope I've convinced you that SAT solvers are at least something to think about. If your problem can easily be reduced to SAT, then I would encourage you to do this because, well, first of all, you get the verifiability, but also SAT solvers have been made very, very efficient. It's very hard to beat them at search because over decades they've implemented all these clever search routines. Unless you have that kind of time to put into your own search, probably what you write is not going to be as fast as a SAT solver. So don't reinvent the wheel. The downside of the SAT solver, of course, is it can be painful to encode things into SAT, right? SAT is very, very primitive. So not all problems, especially ones with like complicated mathematical constraints, can be encoded into SAT. I've done some work on this to help solve that problem and encode other problems into SAT, but still using the SAT solver core as your search engine. You can basically hook up a SAT solver to a computer algebra system and call out to the computer algebra system for like the high level mathematical functions, but keep the SAT solver executing its search. I won't go into details, but check out my website if you're interested in that. We have a lot of work in that vein, and I'm happy to take any questions right now. So thank everyone.